Lesson 15 is key features from graphs of quartic functions. So we've done pretty much this same lesson before with quadratics and with cubics, but now we're moving on to a new type of function, which is the quartic function, and that's just something with a degree of 4. So up at the top, 15.1, a quartic function is a function in which the highest degree of the variable is 4. So there is a standard form. It's kind of just in addition to all the standard forms you've learned before, where we know we're starting with the highest power first and we go down from there. So it's f of x equals ax to the fourth plus bx cubed plus cx squared plus dx plus e with a constant at the end. So just a reminder, I know we've talked about multiplicity before, but I want to just kind of introduce it again with this lesson. So multiplicity, or multiplicity of a root, or multiplicity of a zero, is the number of times that the linear factor corresponding to the root appears in factored form, or in the factor form of the polynomial. That doesn't have to mean a whole lot just as is, but we are going to get into like a couple of examples of what they look like on a graph. So there's two different like types. There's odd multiplicity, there's even multiplicity, because you can have odd or even powers. So when it says like number of times that the linear factor corresponding to the root appears, that's referring to, like, if you look at these functions, for example, like some of these are raised to a higher power, so they're appearing more than once. Like if we were to like expand this would be like 3 different x minus 2's within that function, so it's appearing 3 times. Okay, so looking at odd multiplicity. So odd multiplicity, the function crosses through the x-axis at the 0. For any odd multiplicity that's greater than 1, the graph will flatten out. So this function right here is not a cubic function, but it's just like a good one to look at what multiplicity does to the graph. So there's I said cubic function, but it's not a quartic function. Either way, it's neither of those types of functions, but it's a good one to look at what multiplicity does, or what different multiplicities do. So if we look at what the like zeros are that are coming out of these factors, this x minus 1, if I were to like set that equal to 0, I would add the 1 over, and that would give me an x equals positive 1. And then same thing, or same idea with the x minus 2. If I were to set that equal to 0, I would add the 2 over and get x equals 2. And then for x minus 4, that would give me an x equals positive 4, because I would have to add all the like numbers over. And remember, we find the zeros by like setting each factor equal to 0, and we can see these zeros or roots on the little graph. And this is like a really small snippet of the graph, but this is a root at 1, this is a root at 2, this is a root at 4, sorry. So if we look back at all the multiplicities now of each factor, this one doesn't have an exponent, so the exponent would be 1, the multiplicity would be 1. This one, the exponent is 3, multiplicity is 3. This one, multiplicity is 5, or exponent is 5, multiplicity is 5. So they all have an odd multiplicity. Those are all odd powers. So that's why, like, at the spot at the x-intercept of those points, it crosses through there every single time. Like we cross through right here, cross through right here, cross through right here. And then the kind of different shapes that they're taking goes back to like this part right here. So for an odd multiplicity that's greater than 1, the graph will flatten out. So if we look at like when the multiplicity was just 1, that was my x equals 1, it just crosses straight through that. No like bends, no curves. For the x equals 2, my multiplicity was 3, and you can see it doesn't go straight through 2, it kind of like bends through it. And then for when x equals 4, my multiplicity was 5, so it was even like higher, and you can see it flattens out even more through that 0. So those are just kind of like the different things that happen as multiplicity changes. Notice that because they're all odd though, they are all crossing through, and then we're going to look at on the next graph what happens when they're even. So odd crosses through, and then just keep in mind the higher the power, the more it's going to kind of flatten out as it crosses the x-axis. Okay, and then even multiplicity. So when there's an even multiplicity, the function bounces off the x-axis at the 0. For an even multiplicity that's greater than 2, the graph will flatten out before it bounces back. So same concept of like flattening out with the higher powers. So if we look at this function, and this is just another random function, it's not a quartic or anything like that. f of x equals x minus 1 squared times x minus 5 to the fourth power. So this factor right here, x minus 1, if I set that equal to 0, that would give me an x equals positive 1. This one right here, if I set that equal to 0, that would give me an x equals 5. So finding the zeros, I know I'm going through this kind of quickly, but it's something that we've covered in the past. So we end up with x equals 1 and x equals 5. The multiplicity on both of those is even. So on the x equals 1, it's 2, and on the x equals 5, it's 4. So if we look at those two intercepts on the graph, you can see, okay, this is at 1, and then this is at 5. And they're both even, so 2 and 4 are both even. So they do bounce off, that's correct, where it's like just bouncing like that, bouncing like that. The only difference is, as the power gets higher, the more it kind of like flattens out along that point as well. So you can see that it does get flatter around the intercept of like x equals 5 because the multiplicity was a higher even number. Okay, and then just keep in mind this is a really small snippet of the graph, so there is a whole lot of other things going on in the graph, but I just wanted to zoom in and focus on those x-intercepts. Okay, so main thing here between the multiplicities is just a reminder of what happens when it's odd, what happens when it's even, and then just kind of noticing the differences between what happens when the power gets higher and how it does flatten out around those roots. Okay, so example 1, find domain and range of the function represented by the graph, then write a rule for the function. So remember a domain, when we're thinking about a function, it's just like, okay, what x value can I put in, what input value can I put in, and get a real number out. So at its like most basic form, or like the parent function of a quartic function would just be f of x or y equals x to the fourth, and you don't need to write this down or anything. So I can put any number in for x, and I will get a real number out, because I'm not like, when I say real number, I mean like as opposed to like an imaginary number that you would take from like taking the root of a negative. So any number though raised to the fourth power is still a real number. Obviously it'll be like pretty big number or pretty small number depending on what you're putting in for x, but it'll be real. So that means our domain is all real numbers. And then if we want to find domain by looking at the graph, we're looking at how far does it extend to the left and to the right. So you can see like on the left side of the graph, it's like it's going up and it's going left. It's getting like pretty vertical. But functions will never be completely vertical. Like they wouldn't be functions if that was the case. So we'll never go completely up and down. So this graph is always inching to the left. And then on the far right side, same thing, it can never go like perfectly vertical. So it's always inching to the right, even though like kind of at the tail ends, it does slow down how quickly it's going left and right. But it is going left and right forever, so it's covering all possible x values. So the domain would be all real numbers. I'm gonna write it in interval notation. So between negative infinity and positive infinity. And then remember, interval notation, we use parentheses or brackets depending on if we can include that number within our interval. We can't include infinities since they're like not actual numbers, so we just put parentheses around those. And then range is what my possible output values are. When you're looking at a graph, it's how far can the graph go, like extend up or down. So we can see that, our graph is going up for forever, for sure. But is it going down forever? Like, is it going to cover all these possible y values down here or output values down there? It's not, because we can see, okay, like it goes down to this point, turns back around, goes down to this low point, turns back around. And then like at these sections of the graph right here, it's not going to change directions anymore beyond that. It's just going to continue up and up and up. So that means that our range is limited. So we want to find the lowest point on our graph. So there's like a low point right here, but this point right here is even lower. So that lowest point is kind of like our limit, our lower limit for the range. So we look at what the height of that point is, because range is like the height, not the height, oh yeah, height, and like the possible y values or possible output values. So we just care about the y value here, which is that negative 54.3. So negative 54.3, that's the lowest point that we can have. And then we go up from there. So the way that we would write that with interval notation, it would be from negative 54.3 to positive infinity. So we're starting at a number that's like our lower limit, negative 54.3, and we're going up. So we're going up to infinity, up forever. And then we put a parentheses around infinity. And then negative 54.3 is included within the range because we have a point exactly there. So it's within our function, it's in our graph. So we would put a bracket around that. Okay, and then now if we want to write a rule for the function, so the easiest way to write a rule when you know the x-intercepts is to write it in factored form by finding the x-intercepts. So let's see, I'm going to erase some of these and just highlight the x-intercepts. So it looks like we have 1 right here, -4, -2.5, 0, and 3. So all of those x-intercepts are their roots, their zeros. Remember, all those things are interchangeable. So they're like solutions to the equation version of this function. So I'm going to write them as solutions. So it's just whatever the x value is. So this would be like x equals -4, x equals -2.5, x equals 0, and x equals 3. So x equals -4, x equals -2.5, x equals 0, and x equals 3. So if those are the zeros, we have to think about what factor would create those zeros. So like kind of solving backwards, like when we have something in factored form, like right here, we would set that equal to 0 to get x equals 1. This time we're starting with the x equals 1. We want to get to that factor of x minus 1. So sometimes you can do it in your head. If not, the like kind of trick is to try to get the like these little mini equations equal to 0. So like if I wanted to get 0 on one side, I would have to add this 4 over. So I would do x plus 4 equals 0. So then now this x plus 4, that's the factor that gets set to 0 that gives me the solution x equals -4. And then we just do that same process for the rest of them. So like I want to get 0 on the right side, so it'd be plus 2.5 plus 2.5. So it'd be x plus 2.5 equals 0. So then now the factor is x plus 2.5. I set that equal to 0. Working backwards would give me this solution. So the factor that I'm concerned about is that x plus 2.5. This one was the x plus 4. This, like x equals 0, is like already equal to 0. There's nothing else for us to do there. So then the factor that gives me x equals 0 is just x. It's just the side of the equation that does not have the 0. That's the factor that we set equal to 0. That gives us the correct solution. And then the last one for the 3, I would have to subtract over the 3. And then I would get x minus 3 equals 0. So then the factor that gives me that solution is x minus 3. Okay, so these are all now the factors that get us these x-intercepts that are on our graph. So let's take those factors, put them into like factored form, and we'll start to kind of create a function that way. So we're going to say, you can use f of x or y, it doesn't matter. Just make sure you're comfortable with both, depending on like what kind of answers are presented to you in any kind of like multiple choice problem. So I'm going to take all 4 of my factors, all the ones highlighted in yellow, and multiply them all together, but not like actually FOIL, just write them multiplied together. I'm going to put the like x first. We usually put like the single one in front. So it'd be x. And then next I'll do the x plus 4. And then, and the order doesn't matter here. Next I'll do x plus 2.5. And then next I'll do the x minus 3. And again, order does not matter at all. You really don't even have to put the like regular like x in front. It can go anywhere within that like product. Okay, so now what we've done is we've written a function, and this is not the final answer yet, but this function is a function with the same x-intercepts as our graph. However, there can be many different functions that have the same x-intercepts. So we have to find something that ensures that it goes through like all the exact same points. And like algebra, we use like the word stretch to talk about like how the function is kind of like transformed, moved one way or another. kind of like how slope is in Algebra 1. It's not the same thing, it's not like a consistent rate of change, but it's the same idea. So to find that number, it's going to be a constant out in front of the function, and that's just going to make sure that we go through all the exact points. We use the letter A. So I'm just going to put an A out in front. That's a really big A. I'm just going to put an A out in front, and then that's multiplied by everything else. Okay, and then now we need to pick any point that's on our function that is not an x-intercept, and we'll take that point, we'll put it in for x and for f of x, and then we'll be able to solve for a as our only unknown. So if we're looking at all the points that are on our function that are not x-intercepts, they're kind of funky points. Like there's this negative 1.2, 18.4, negative 3.4, negative 11.8, and then 1.9 and negative 54.3. So we can certainly use those for like x and f of x, and it would give us what we need. In the workbook, though, around this part of the problem, they do pop up like a little bit cleaner point, so we'll go ahead and use that. It was not on the original graph. It's the point negative 5, 100. So I'm just going to put that on really quick. It's about right here, and they have it labeled, so it's exact. So negative 5, 100. And like I said, the points, like the non-x-intercept points, the ones that are highlighted in yellow right now, like those would work. They're just kind of ugly points to work with. So we'll use a little bit cleaner one. And any, like you can use any point that you know for sure that's not an x-intercept. Okay, so we're going to put the negative 5 in for all of the x's. So we'll put negative 5 right here, right here, right here, and right here. And then we'll put the 100 in for f of x or y, depending on what you used. So the 100 will go in for f of x. And then that leaves a as our only unknown, so we'll be able to solve for it. So it would look like 100 equals a, and then times x, so times negative 5. And then times x plus 4, so negative 5 plus 4. Times x plus 2.5, negative 5 plus 2.5, and then negative 5 minus 3. So we took all of our x's, they just got all replaced with these negative 5s, and then the f of x got replaced with 100. And then now we need to like work on simplifying the right side of the equation. I'm gonna go ahead and zoom in over here. We don't really need the graph so much right now. So this will be a 100, and then equals a times, I'm going to leave that negative 5 right there for now. And then if I add negative 5 plus 4, that's negative 1. Negative 5 plus 2.5 is negative 2.5. And then negative 5 minus 3 is negative 8. Okay, so this is 100 and then equals a times, I'm going to go ahead and just multiply all these together now. If you don't want to worry about like putting the negatives in a calculator or something like that, you can just count how many you have. If you have an even amount, it would be a positive product. If you have an odd amount of negatives, it would be a negative product. So we have like 1, 2, 3, 4 negatives, so even amount of negatives, so it'll be positive. So we can just multiply 5 times 1 is 5 times 2.5 is 12.5 times 8 is 100. Okay, and then now we have 100. Our goal is to get a by itself. We have 100 that's being multiplied by a. So I would divide both sides by 100. And then 100 divided by 100 is 1. It's equal to a. So we end up with just a equals 1. We just have to take that 1 and put it back into the function where a was, which will give us our final answer. Which was technically what we started with, but that's not always the case. We just have to make sure that we are going through the correct points. We have that correct a value for the function. So I'm going to take that a equals 1, put it in for a into my function. It'll be f of x equals 1 times x, and then times x plus 4 times x plus 2.5 times x minus 3. And then of course, if you don't write the 1 in front, it means the same thing. So we'll just leave that 1 off. Like I said, it's not always going to be 1, so you would go through the same process to find what a is, regardless of what it is. So f of x equals x times x plus 4 times x plus 2.5 times x minus 3. Okay, so example 2 is kind of like a repeat problem, just a different function, so just another practice here. So if you wanted to like pause the video and see if you could do it on your own, this would be a good time. It'll be the same set of steps, it's just like a little bit different because we only have 1, 0. So example 2, find domain and range, and then write a rule. So same thing applies here. The domain is always going to be all real numbers for a quartic function, unless there's some sort of domain restriction given by like a real life problem, like a word problem. But we don't have that, we just have the function, so domain is all real numbers. So it goes from negative infinity to positive infinity. And then the range is limited. You could see that there's a low point right here. We just, for range, we only care about the y coordinate, so it's 0. And then it goes up from there. So if we're like starting at 0 and going up, that would be 0 to infinity. And then a 0 is included within the range because we have a point there, so we'd put a bracket around 0 and a parentheses around infinity. And then moving on to like writing the equation. So we only have one intercept, so only 1, 0. Remember, it's like, I know they're the same number, but it's just whatever the x value is, that's our 0. So we would have 1 at x equals 0. And then we have to think of the factor that would create that. And to do that, we usually like try to get like one side equal to 0. So that means that the factor that gives you that 0 is just x. And then we have to think about, okay, I have, like, this is a quartic function. It's supposed to be a quartic function, it's supposed to be x to the 4th. I only have one factor, so there must be like some sort of weird multiplicity thing going on that's not only causing me to only have like one factor, but also causing the like graph to bounce right there. So if we look back through like at example 1, all of these x-intercepts, the graph crossed through. It crossed through at -4, at -2.5, at 0, and at 3. And the multiplicity on all of our factors was 1 because it crossed through on every single one, but this is different. So we have just this 1, 0, and it bounces off of it. So if it bounces off of it, it has to either be a 2 or a 4, like a multiplicity of 2 or 4. So we can set up our function like f of x equals, the factor is x, and then if we're deciding between 2 and 4, if I say it's just 2, well, there's no other factors there, so this wouldn't be a quartic function. It would be a quadratic, which I left the wording off, but this is a quartic function. Sorry, I'm going to add it right here. I should have typed it, but I didn't. So this is a quartic function, meaning that it's x to the 4th power, or like if we were to multiply all the factors through, it would be x to the 4th power. Like for example 1, we have 1, 2, 3, 4 x's, so that's x to the 4th power. So that means that our factor has to be to the 4th power because we just have that 1. And then that goes back to like when we first talked about multiplicity, how if you have even, it bounces off. And then if it's like a higher even number, like the higher it gets, the more it kind of flattens out around the 0. And you can see that it's like pretty flat here, like around the 0. It definitely doesn't just like go like that. That would be more of like a quadratic. It's really flat around it. So our factor is going to be x to the 4th. We still have to find the a value, even though it's just like kind of simple like this, or we still at least have to like try to find one in case there's one that's different than 1. So the way that we find it is the same as like example 1. We take a point that's on the graph that's not an x-intercept. So we have 1 at 2, 16. So we would put 2 in for the x, and then 16 would be f of x. So 2 is going in for x, and then 16 is going in for f of x to solve for a, because that leaves a as our only unknown. So we put 16 into f of x, and then equals a, that's what we're trying to solve for, and then times x is going to become 2, and then that is raised to the 4th power. So goal is to get a by itself to solve for it. So we'll go ahead and start simplifying. I can take 2 and raise it to the 4th power. So this would be 16 equals a. And then 2 to the 4th power means 2 times 2 times 2 times 2, which is also 16. Goal is to get a completely by itself, so I'd have to divide both sides by 16. And then 16 divided by 16 is 1. And then 16 divided by 16 over here, that cancels out. So I'm just left with a. So same kind of situation here. So I have the like a equals 1. I would take that, put it in here for a. So my like final function would be f of x equals 1 x to the 4th. And then of course we don't have to put the 1 there. We can just leave it off if we prefer. I try to stick with like the examples in the workbooks to keep it like consistent, but I'm a little bit bummed that they gave us both a equals 1. Just know that like even when a doesn't end up being 1, this process is exactly the same. And either way, if it's 1 or not, we always have to like check to see exactly what a should be. Okay, so 15.2, this is identifying like all these key features of these same graphs that we were just looking at. So example 1, we're going to find end behavior, relative max and min, where it's increasing or decreasing. So for end behavior, remember that's like which way is the graph finishing, up or down. So for the first line, as x approaches negative infinity, that's the left side of the graph because all the x values are getting smaller. What is f of x doing? So the left side of my graph is going upward. So that means that f of x is approaching positive infinity because that means up. And then the second line, as x approaches infinity, that's to the right because all the xy's are getting bigger. On the right side of my graph, it's finishing up as well. So it should be going, f of x should be going to positive infinity also. So one thing to keep in mind for like quartic functions, it's just like quadratics where they should be finishing going in the same direction. So up, up, or down, down. So it's kind of an easy way to like check your work a little bit. If you're like answering that one is going to positive infinity and one is going to negative infinity for a quartic function, you want to re-examine it. Okay, so next is relative max. So remember those are like anywhere where there's a change in direction, there's a relative max or relative min. So if we kind of point out like where all the changes in direction are, there's one, like we're going down and then we're going up. So we have a change in direction right here. We're going up and then we're going down. So there's a change in direction right here. And then we're going down and then we're going up. So there's a change in direction right here. So every like little peak or low point, that's a relative max or relative min. The relative max is the kind of peak, like top of a little hill. So that would be my like negative 1.2 and 18.4. The max is referring to the height of the point, like what is the maximum height there. So we just care about the y coordinate for the relative max. So just the 18.4 would be my relative max. And then for relative min, we have like two different little low points right here. So we have at a negative 3.4 and negative 18, no, sorry, negative 11.8. We have a low point because it's like kind of at the bottom of the point surrounding it. And then also at 1.9 and negative 54.3, there's a low point. There's a point that's like lower than the point surrounding it. So because we're talking about just like relative max and relative min, we do have to mention both. So if it was just like overall minimum, it would definitely be like the lowest point out of the two. It would just be that 1.9 and negative 54.3. And there wouldn't be a maximum if that was the case, but we're just talking about relative. And so if that's the case, every single change of direction has either a relative max or min. We just list both. So for the negative 3.4 and negative 11.8, again, we're looking at the height of that point, like what's the lowest height there. So that would be just negative 11.8. And then we would just list the second one. So at 1.9, negative 54.3, again, just the height of that point, which is negative 54.3, just whatever the y coordinate is the height from the point. So negative 54.3 are both relative maxes, or relative minimums, because they're the lowest point relative to the point surrounding it. And then for where the function is increasing or decreasing, we have to follow the graph from left to right. So I know that this function is like increasing overall, like, you know, both sides go upward, but there are sections where it's increasing versus decreasing. So to find those, we follow it from left to right. So if we start on the far left side, going downward until we hit that point. So that would be a decreasing section. And then, let's see, after we hit that like change of direction point, we're going upward. So that would be an increasing section right here. And then after that negative 1.2, 18.4, we're going downward. So that would be a decreasing section. And then after that 1.9, negative 54.3 point, we flip back up and we're going upward and we finish going upward. So this would be an increasing section. So the blue sections are increasing, the pink sections are decreasing. I'm just going to kind of color code it. So blue is increasing, pink is decreasing. And then because we're following the graph from left to right, the x values of the points where they're changing direction become our boundary lines. So like if I wanted to describe this first increasing section right here, one that's highlighted now, I would have to look at the 2 points that it's increasing between. So that's this point right here and this point right here. And then because I'm following from left to right, the x values become the boundary lines. So I'm just looking at the x values between those 2 points. So that's the negative 3.4 and the negative 1.2. So it's starting to increase at negative 3.4, and then it stops increasing at negative 1.2. And then this is interval notation, so we have to do like brackets or parentheses. At those points where changing direction, it is not increasing or decreasing, like it's completely neutral. So for writing like intervals for increasing and decreasing, you wouldn't use brackets because the points are not included within increasing or decreasing because they're just in the middle. Okay, so that's the first section. I'm going to erase some of this. And then the second section where it's increasing, it finishes off over here. So it starts increasing at this point, and then it's everywhere to the right of it. So if it's everywhere to the right, we're going to go to infinity. We have to look at like where it starts increasing, and we have to look at the x value, which is 1.9. That's where it starts increasing again, and then it just finishes like increasing, so everywhere to the right. So we'd say and 1.9 to infinity. So the number to infinity just means like to the right of the number. If we did like negative infinity to the number, it'd be to the left of the number. So that's for increasing, and then for decreasing now, let's do this section first. So it's decreasing like everywhere to the left of that point right here. So everywhere to the left would be like negative infinity until that point, and we just have to look at like what is the x value of that point. It's negative 3.4. So we say decreasing from negative infinity to negative 3.4. After that it changes. Parentheses around both. Of course around negative infinity, and then negative 3.4 is neutral, so it's not included within that decreasing section. And then next we'll do this little section down here. So we're looking at where are the points that are like kind of causing it to change direction. It's changing from increasing to decreasing right here, and then decreasing to increasing right here. So we're just looking at the x values, negative 1.2 to positive 1.9. So negative 1.2 to a positive 1.9. And then remember that like with any section of where it's increasing or decreasing, if it's just like all the way to the left or all the way to the right, those are the ones that involve infinity. Versus if it's between like two kind of stagnant points on your graph, like these two kind of middle ones are right here and then right here, those are the ones that are between the exact values because they're in between set points and not just like everywhere beyond a certain point. Okay, so example 2, this is the last one. This is just finding like the same information from that second graph that we did in 15.1. So find end behavior, relative max, min, increasing or decreasing. So end behavior is how the graph is finishing. This graph is finishing the same way as the last one. Technically, both sides are going up, so the end behavior would be the same. So as x approaches negative infinity, that is left. F of x approaches, that means is the graph going left is the graph going up or down? So our graph goes left and up. So f of x would be approaching infinity. And then as x approaches infinity, that's the right side of the graph. So the right side of my graph finishes going up. So f of x approaches infinity as well. And then just a reminder for any quartic function, these are all quartics for this entire set of notes. They should both be going in the same direction. Okay, the only thing that would change end behavior for a quartic function is if, for the graph, it was facing downward, just like a quadratic, with a negative a value if you're looking at the function as a negative lead coefficient. So relative max, remember that we only have a max or a min, a relative max or a min, where it changes direction, and we only have one change of direction for this graph. It's at 0, 0. So that's not, it's definitely not a max, and we don't have any high points or peaks because the graph just keeps going up forever. So this one doesn't technically have a relative max. So we would just write none. And then for the relative min, we can see that 0, 0, that's definitely a low point. And I know they're the same value, but just a reminder, we care about the y value from that low point, which is 0. So we would say we have a relative min at 0. It's also technically a minimum overall, kind of like what you see with quadratic. So it goes both ways. And then for where the function is increasing or decreasing, we're following the graph from left to right. So from left to right, we are going down, 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 down until we hit 0, 0. And then after that, we are going upward. So for this section, the pink one, we are decreasing. So we're going downward as we follow from left to right. And then after that, the blue section, we are increasing. So we're going upward from left to right. So for increasing, we start off increasing, and again, I know that these are the same numbers, 0 and 0, x and y are the same, but remember when we're looking at where it's increasing or decreasing, we're looking at the x value where it's changing, because we're looking from left to right. So after that x value of 0, it starts increasing, so it's increasing everywhere from 0 to the right. So 0 to the right would be from 0 to infinity, and then 0 is neutral, it's not increasing or decreasing there. Infinity cannot be included because it's not a number. And then for where it's decreasing, it is decreasing on the left side of the graph until we get to x equals 0. So everywhere to the left of x equals 0, that's negative infinity to 0. Parentheses around negative infinity, parentheses around 0 because 0 is neutral. And then that's it. So I know there's a bunch of different kind of things to remember with increasing or decreasing. Main thing is that the x values of the points we're changing direction are going to be a big part of your boundaries.